I am John McGowan. I may be able to solve your problem using mathematics and mathematical software. Mathematics and mathematical software, combined with today's powerful computers, can deliver large improvements in speed and efficiency, as well as new, useful features. Mathematical software is in widespread use. Digital video such as YouTube and Skype, digital audio such as MP3 files, JPEG images, speech recognition, computer-generated images in movies and video games, and the Global Positioning System, or GPS, that tells people where they are, all multi-billion-dollar markets today. Mathematical software may offer solutions to many pressing problems ranging from big problems such as the current energy crisis by, for example, locating new oil and natural gas deposits through the analysis of methane in the atmosphere, a common product of underground oil and natural gas, to small problems such as the need to relax, with entertaining new audio-video effects for computer games and movies.
Hello everybody, I'm speaking to you today from a UPS customer center in Landover, Maryland, where I came to talk about an issue that's affecting families and businesses just like this one, the rising price of gas.
I may be able to solve your problem with mathematics and mathematical software. The successful solution of your problem using mathematics and mathematical software requires three things. 1. Realistic expectations about the size and scope of mathematical software projects. 2. Clear thinking and honest objective measurement of the performance of mathematical software. 3. A professional working relationship based on mutual respect that recognizes the complexity and special challenges of mathematical software development. The rest of this presentation explains these three essential components needed to successfully solve your problem with mathematics and mathematical software. Mathematical software development is an uncommon area, unlike mainstream software development such as business websites and so forth. I have found it filled with misconceptions, frequent lack of critical judgment, and questionable claims. I frequently encounter individuals and groups with extremely optimistic ideas about the scope and risk level of mathematical software projects. Examples include the CEO of a highly successful company who thought a project that I would estimate to take at least 6 months was a 2-week project. Many people appear to be unaware of the size and complexity of various commonly used examples of mathematical software. For example, the widely used open-source X264 H.264 video encoder is over 62,000 lines of code, developed between 2004 and 2011 with at least 18 contributors. The H.264 video compression standard is the video compression used in many YouTube videos, Blu-ray discs, and other high-performance video systems. The popular open-source independent JPEG group, JPEG Image Encoder Decoder, is over 52,000 lines of code, developed between 2000 and 2011 with at least 13 contributors. The lame MP3 audio encoder, best known as the MP3 encoder plugin for the Audacity audio editor, is over 87,000 lines of code, about 40,000 lines of algorithmic, mathematical, C, C++ code, and about 47,000 lines of Bourne Shell installer code, developed between 1998 and 2011 with at least 9 primary developers and at least 21 total contributors. As a point of reference, the Space Shuttle main engine, one of the most sophisticated engines in the world, has about 50,000 parts. These mathematical programs are comparable in complexity to the most sophisticated physical machines in the world, and often fail catastrophically due to tiny errors just as a rocket engine will. Software engineering expert Barry Boehm's original software cost estimating model, COCOMO Embedded, which stands for the Constructive Cost Model for Embedded Software Development, appears to give a rough estimate of the time it takes to develop these low-level mathematical programs, although there is substantial variation between estimates and actual effort. COCOMO is, at best, accurate to within a factor of 3 of actual effort. About half the people that I have talked to about potential full-time jobs or contract projects have had extremely optimistic ideas. It only makes sense to talk further if a potential employer or client is thinking in the same ballpark as myself. That ballpark is 1,000 lines of code is predicted to be 3.5 man-months. 2,000 lines of code is predicted to be 8.3 man-months. And 5,000 lines of code is predicted to be 24.8 man-months. I also frequently encounter a lack of critical judgment and questionable claims, frequently in the form of technologies that simply do not work at all, or perform much less well in realistic field conditions than claimed. For example, speech recognition with a claimed accuracy of 99% and an actual accuracy of 95%, which in practice is a very significant difference. In speech recognition, there have been several notorious scandals, including Kurzweil Applied Intelligence and Lernout and Housby. Some of the claims of Ray Kurzweil, the founder of Kurzweil Applied Intelligence, and a speech recognition researcher, have been widely questioned. See the recent movie Transcendent Man, available on Netflix, for a fair but friendly portrait of Ray Kurzweil. These are some prominent examples of a problem that I have encountered on many occasions. Questionable claims and lack of critical judgment is particularly common if the technology could be characterized as a form of artificial intelligence, AI, machine learning, pattern recognition, and so forth. People often seem to associate magical and mystical ideas with mathematics, whether consciously or not. This lack of critical judgment and questionable claims occurs with individuals and organizations with impressive resumes and credentials, prestigious investors, and/or the support of major government funding agencies such as the Defense Advanced Research Project Agency, better known as DARPA. Organizations or individuals evaluating or undertaking projects of this type should at minimum be able to answer the following questions. 1. Have truly independent, rigorous tests of the performance of the technology under realistic field conditions been performed? What were the results? Is the performance good enough for the intended use? 2. If not, why not? And what are the theoretical reasons for expecting the needed performance in the absence of actual field tests? Is this extremely risky, blue sky, breakthrough research, or are there solid, immediate reasons for expecting success? Questions about the technical feasibility, the scope, and the risk level of projects and tasks within projects arise frequently in mathematical software development. It is not analogous to user interface or website software development, in which, for example, technical feasibility is rarely an issue. For example, during the early 1990s, the high-profile startup Go, Apple's Newton handheld device, and several less well-known efforts relied upon handwriting recognition, which still lacks the accuracy needed for handheld devices today, and therefore failed to develop and market devices similar to the successful iPhones, Androids, and other devices of today. Success would have required proper evaluation of the performance of the handwriting recognition algorithms, the technical feasibility of the designs, and working within the limitations of the known mathematics at the time. Success in mathematical software development requires a working relationship where there is, from the beginning, freedom to discuss the technical feasibility, the risk, and the scope of a project. A client or employer should be able to treat me and my professional judgment as a reasonable person would, for example, treat a neurosurgeon discussing a complex, risky operation to remove a brain tumor in their head. The work is difficult, nitpicky, painstaking, and often requires a very high level of concentration. There is a higher proportion of debugging than in many other types of software development. Mistakenly undertaking a project or task that is not technically feasible, much larger in scope than estimated, or much riskier than estimated, is invariably costly and often results in failure. A mature professional relationship based on mutual respect and frank discussion of management-level issues such as technical feasibility, scope, and risk is necessary for success. Mathematics and mathematical software can deliver large improvements in speed and efficiency, as well as new, useful features. Success requires realistic expectations for the size and scope of mathematical software development, clear thinking, and objective measurement of performance, and a professional working relationship based on mutual respect in which the complex technical issues, the technical feasibility, the scope, and the risk are discussed freely. With these three components, and depending on the technical details, I may be the solution to your problem.